Hi everyone, my name is Brahman Harla and welcome to my first session of the analysis of training object detection models with synthetic data. So object detection models, they require a lot of annotated data, and creating this data manually is a very costly process and it can also introduce errors. Recently, a lot of people have tried using synthetic data for this because synthetic data, you can easily render a good looking image of an object and get the annotation for free, and also the annotation is very correct. But there is a difference between those rendered images and real images. And this leads to worse performance on the object detection models because of this thing called the domain gap. In this work, we want to investigate how we can decrease this domain gap by potentially making the synthetic data more closely match the target domain, by making the synthetic data poses more closely match those of the real data, as well as the lighting conditions. Um, and we look at this in a holistic manner where we also look at different deep learning techniques that have been used to improve generalization over the years. For this, we use a very unique data set called the data set of industrial metal objects, and it contains a set of real metallic objects, a number of different poses, five different objects. It also has an exact synthetic clone of this data set, so each image has its own synthetic clone. Additionally, it contains a subset where those images, same images are with the same poses, but where there's a lot of different lighting conditions randomized. And there's also a subset where the lighting conditions are kept the same, but the poses are randomized. And there's also a subset where both of those factors are randomized. And what we can do with this data set, this allows us to train a number of models and look at the how those different variations impact generalization in an isolated manner. So we can look at these variations separately and say, okay, they help for generalization on real images. For this, we trained a number of mask RCNN models. We trained those and then we tested their performance on a test set of real images that was always unseen during training. Important is that we always train for 1,000 images for each epoch because those data sets have different sizes, so we can compare on a fair manner after a number of epochs. The more details about this are in the paper. So for results, for our first experiment, we had the question like, does it matter the scene composition? Does it matter to have random light? Should we try and match light conditions? Should we try and match poses? So we trained a number of models on those data sets I mentioned earlier, and we then tested their generalized, how well generalized in real images. What we can say is that when we the, when we match light and poses, um, so this is actually the worst performing data set of all of them. The data sets that do perform well are the ones in which we randomize light conditions. So, so the ones with real light conditions actually are the worst. This indicates that there's it's just probably very difficult to accurately simulate the light. So it's very difficult. So there's a mismatch in low-level features, which which makes in turn better to just randomize it, um, where the wide distribution of light conditions actually leads to better generalization. We repeated the experiment with, or we took the we restricted the data set size to be the exact same for each of the models, and we again see that the models for randomized lighting actually are the best, and that now the model that has randomized poses and real light is the worst, actually very bad. But for we now are wondering, because this is not a real scenario, in real life we've shown that transfer learning and data augmentation are two popular techniques that improve generalization ability. So we repeated this experiment, but we audited these techniques to see what their effects would be. And then when adding these techniques, we see adding data augmentation immediately boosts the performance of the two models with real lighting conditions. So the added variation from data augmentation, it actually improves generalizability. But again, it's not, the models do not perform great. But then when we use transfer learning, we see there's a very large boost. And a very peculiar thing is that now the model, which was the worst in the previous experiment, now is the best. So this model does real light and real poses, now is the best performing model. So when we equip a model with weights that were already trained on a different data set on real images, we see that it now is able to benefit from those real lighting conditions that we modeled. So the general trend we see here is that the models with trained on real poses are the best. And again, when we repeated the experiment while restricting the dataset size, and we see it again. We see the same trend. So we see here that transfer learning gives a very large boost in performance. So we want to look at that a bit more closely. We want to see, like, transfer learning, which layers should we retrain really. And one experiment we had is that when we retrain all of the layers of a ResNet, as opposed to retraining only the heads, it gives a very large boost in performance, so only almost 10 average precision points. So another interesting thing here about this experiment is that when we restrict the image size to 1.7K, we see there's only a very small decrease in performance, whereas, for example, the fully random data set in yellow here is trained on 70,000 images, and here on only 1.7K. The decrease is almost nothing. So what we did was we experimented where we took this fully random data set of 70K images, and we trained our model on different subsets of those, and we see here that adding more random images to our data set, it only gives a very small increase in performance, and then even like a decrease in performance. So yeah, when using transfer learning and data augmentation, it doesn't seem like you need a lot of images to improve more. So there's a limit there. And like a final technique that often gets used when using synthetic training data is to try and use real images. So we were wondering how should we use real images and how many should we use. So to answer that question, we train a model on a fixed set of images, fixed number of images, but we changed the ratio of synthetic to real images. So our first model had only synthetic images, and then we added a bit of real images, and then more and more and more, until we have a 50-50 ratio. So you can see that when adding real images in a 20:1 ratio, so in total we have 3,500 images here, we can see a huge leap in performance. And there's still still some performance increase when increasing the ratio, but it's actually very limited. What we also did was we checked whether it would be better to mix them in one data set or to train on the synthetic images and to fine tune on the real images. And there is a big there's benefit to fine tuning. So here you can see only a small amount of real images and a very small ratio gives a very good performance boost already. So the main takeaways of these are that recreating the target domain in terms of object detection, in terms of object poses and lighting conditions is actually helpful. But what you should do is you should use transfer learning to allow your network to interpret these low-level features and to really benefit from recreating the light conditions. So modeling object poses, it gives better performance increase than trying to model lighting conditions because it's easier to recreate the high-level features such as object pose in a simulator. Other research found that when transfer learning, you should freeze your feature detection network so your network doesn't learn from the synthetic data on low-level features. We show that for this case, really, you could retrain your entire network, and it is actually better. So we try to say that you look at this on a case-by-case basis because it could be better to retrain your entire network. And then finally, other work suggested that more and more randomization would lead to better generalization. But we concluded for this case it's actually better to add more relevant synthetic images. as opposed to add more random static images. What even the best is to would be to add real images, and when doing so, using fine tuning. So thank you for your attention. I hope you enjoyed this. If you have any questions, you can see my email address here. Don't hesitate to contact me. Thank you a lot.